Swayam Prabha. Digital India. Educated India.
Welcome to the next session on Organic Chemistry Paper 2. This is the last session in this particular module. In the module 8, we are studying about aryl halides and phenols. In the last lecture, we will be studying about worked out examples of aryl halides and phenols. I am Dr. Balaji, currently working as Associate Professor in the School of Biotechnology at Jawaharlal Nehru University. This project is sponsored by DTH Swayamprabha, MHRD, New Delhi. The topics that will be covered in this particular session includes worked out examples of aryl halides and phenols. We will be studying about various reactions and interconversions of phenols and other derivatives. Let us study about some problems related to aryl halides and phenols. We will study some worked out problems. The first one is how to prepare the following compounds from benzene. We have a dibromo derivative and we have a tribromofluoro derivative. As shown here, we need to find out how these two compounds can be prepared from benzene. So we can start from benzene. Treatment of benzene with acetyl chloride and AlCl3, that is the typical Friedel-Crafts reaction, Friedel-Crafts acylation reaction. That gives the diacylated product, but this is a very difficult process, although it may happen because the introduction of the first acetyl unit generally deactivates the aromatic system from further acylation, but acyl group is a meta-directing group, so under harsh conditions or with a very high temperature and presence of acid chlorides, we can make this reaction give the disubstituted product, and this disubstituted ketone on treatment with KMnO4 and heating at high temperature produces the corresponding dicarboxylic acid, and we can follow the Hunziker reaction. Once we make the dicarboxylic acid, we can convert that into the silver salt, followed by treatment with bromine produces the corresponding dibromo derivative. So this is one method by which a carboxylic acid can be converted to bromo using Hunziker reaction, and Friedel-Crafts acylation reaction is also employed. So these are all the two name reactions which can be employed to make the corresponding dibromo derivative. And for this particular one, we are actually starting from the amino derivative directly. So this aniline can be prepared from benzene using couple of steps. Benzene can be converted to the nitrobenzene using nitration reaction. The nitro derivative can be reduced to obtain the corresponding amino derivative, that is the aniline can be prepared in two steps from benzene. This on treatment with the bromine water, as we know in the electrophilic substitution reaction, any activated groups like a phenol or the amine which are electron rich and which are activating the aromatic system leads to tribromo derivative. So we are making use of the activation of aromatic ring with the help of the amino group. So that leads to the tribromo derivative efficiently. And now our only job is to convert the amino group to the corresponding fluoro derivative. So we already know the fluoro cannot be directly prepared by the direct halogenation method. and the diazo route is the best one. So we can actually convert this amino to the diazo compound using nitrous acid at 0 degree, and this on treatment with NaBF4, basically BF4 minus, produces the corresponding fluoro derivative. So for the preparation of the fluoro, you have to always remember diazonium route is the best one to prepare. So always remember that if we have to prepare a fluoro-aryl systems, aryl fluorides, the diazonium route is the best one. So to introduce the diazonium group, we need an amino group. To make the amino group, we need the nitro group. So that way you can actually plan that sequence of reactions. Now we have a dichloro-nitro derivative as shown here. We need to identify the product formed in the following reaction, and we also need to give a suitable explanation for the product formation. So this is nothing but we have a strong nucleophile OH minus. We have a good leaving group, so that means we can actually expect a nucleophilic substitution reaction. Moreover, we have a nitro group, which is an electron withdrawing group, that also facilitates nucleophilic substitution. So our job is somewhat reduced, but the only problem we have is we have two chlorines. There is a chlorine group which is para to the nitro, there is a chlorine which is meta to the nitro. So does it mean the nucleophilic substitution will happen at both the halogens or only at one of the halogen? If it happens at one of the halogen, which is the one which will undergo the nucleophilic substitution, we have to identify. So these are all the little twists given in this particular problem. So you have to be very careful when you have para and meta substitutions present for the nucleophilic substitution reaction. So we are going to get a product in which the para halogen is replaced to give the phenoxide salt, basically, since we have sodium hydroxide. So this is formed as the salt. This on treatment with the HCl will produce the corresponding phenol. Now we have to give an explanation why only the para halogen is which underwent nucleophilic substitution and not the meta one. So the reason is we already know the nitro group basically activates the ortho and para positions. In this particular case, we have only the halogen in the para position. So this para position is now activated for the nucleophilic attack. And this halogen also being in the ortho position also activates this chlorine for the nucleophilic attack. So there are two enablers. One is the nitro group which activates its para position, and this halogen activates this carbon by the ortho position. And now the next thing is, if the OH is introduced in the first step, this can in turn activate the nucleophilic substitution on this chlorine. That is one possibility, but unfortunately oxygen, this phenoxide, is a electron donating group. So whenever we have an electron donating group, that basically disfavors the nucleophilic substitution reaction. So after the phenol or the phenoxide is formed, this particular system is now resistant to further nucleophilic attack and the reaction stops here. Now we have two compounds which are both meta disubstituted compounds. Here we have the dichloro derivative, here we have a disulfonic acid derivative. Now our job is to find out between A and B which one will give 1,3-dihydroxybenzene. So that means we have to effectively carry out aromatic nucleophilic substitution on A and B to get the phenol derivative. We already know the chlorine is not easily undergoing nucleophilic substitution unless there is an electron withdrawing group. We do not have a nitro group on this system, so that means this cannot undergo aromatic nucleophilic substitution. So finally that leads to only the sulfonic acid can be easily converted to the corresponding phenolic derivative, as we have seen in the synthesis methods. So compound B gives the corresponding phenol very easily compared to the dihalo derivative. Now we have three compounds. We need to identify how these three compounds can be prepared from phenol and acetic anhydride. So let us start with any one of the compound. Say this is the ester, this is the keto derivative, this is a phenolic ketone. So we have three different compounds and we have to identify which can be prepared very easily. So the first one is treatment of phenol with acetic anhydride in the presence of a base gives the corresponding ester. So this is the ester formation reaction. This is a very simple and straightforward method. So once we have this ester can now undergo Fries rearrangement. So we can do a Fries rearrangement on this phenyl acetyl phenoxide. This ester on treatment with AlCl3 undergoes Fries rearrangement to give the corresponding hydroxy ketone or the phenolic ketone. So this first compound can be prepared from the second compound very effectively. And now we have to remove the phenolic group. The OH group has to be removed. So what is the best method or best way to remove it? This is basically, if we treat zinc dust method, what will happen is this OH group will be removed, but correspondingly the carbonyl group also will be reduced and we will be ending up with the corresponding alcohol and we will not end up with a ketone. So that means we have to identify a method by which the OH can be removed while keeping the COCH3 group. It's very difficult and it is a challenging one. So the best method will be convert the phenol using the zinc dust to the benzene. First we have to remove the OH group, then we can introduce the COCH3 group by the treatment of AlCl3, that is the Friedel-Crafts acylation of acetic anhydride on benzene gives the corresponding acetophenone. So this is nothing but the acetophenone. So this can be formed by this Friedel-Crafts reaction. So from the phenol we have to make first the benzene, and from the benzene we can make this corresponding acetophenone. We have four compounds here. We need to identify the compounds in the increasing order of acidity and we have to reason out why we are putting that. We have a phenol, we have a ethanol, we have cyclohexanol, we have di-tertiary butyl phenol. So we have four different compounds. We have two phenols. We already know phenols are more acidic than the alcohol. So we can easily identify these two may not be highly acidic compared to these two. Now we have to find out whether these two are having similar acidity or different acidity. So basically the arrangement of order is C is the least acidic one, A is the most acidic one. Now we have to find out why. The C is less acidic because it is a secondary alcohol. So the secondary alcohols are generally less acidic compared to primary alcohols. So that is the reason cyclohexanol is the least acidic one, followed by ethanol. Because of the steric hindrance of the tertiary butyl groups ortho to the phenol, this one does not form the phenoxide ion very effectively, because for a phenol to be acidic it has to form the phenoxide ion very easily. That means H plus has to be removed. Because of the presence of this bulky tertiary butyl group, this proton cannot be easily removed. In other words, this will not give the phenoxide ion very effectively. So this steric hindrance prevents the resonance stabilization. So D is the next acidic one, and A is the most acidic one. That is, the phenol is the most acidic compared to the ditertiary butyl phenol. The next one is we have to convert bromobenzene into aniline, the allyl derivative, and the dinitrophenol and benzyl alcohol. So we have 4 different products we need to form from the bromobenzene. So what are all the different methods we have to use? This is nothing but the simple nucleophilic substitution reaction. So treatment of a very strong base, potassium amide, in the presence of ammonia produces the corresponding amino derivative, that is the aniline is formed. This reaction requires very high temperature. And the next one is bromobenzene can be treated with allyl bromide to give the corresponding allyl derivative. For this reaction also we have to use a very strong reducing agent, that is the sodium metal. This is very similar to the Woods coupling reaction, where the bromo and the bromo can be coupled with the help of the metal sodium. And the next one is the bromobenzene is treated with the nitric acid because we need to make the nitro derivative. So nitration of the bromobenzene gives the dinitro derivative, which on treatment with the sodium hydroxide we already have seen. Even sodium carbonate is sufficient to convert this bromo to hydroxyl because of the presence of 2 electron withdrawing group. And the last one we have earlier seen, the Grignard reaction is the best one for the preparation of benzylic alcohol. So formaldehyde, when treated with the phenyl magnesium bromide followed by acidic workup, gives the benzyl alcohol. So that way bromobenzene can be converted to the various compounds as shown here. Now we need to identify the product formed in this 4 different reaction. So this is a very simple substitution reaction. So the chlorine is replaced by the cyanide group, and in the case of ammonia, we have 2 bromines. One is attached to the aromatic ring, another one is in the benzylic position. So on treatment with ammonia, which one will undergo the reaction? This is a tricky one to answer, but we already know nucleophilic substitution on the aromatic system is very difficult. So this only gives the benzylic substitution. So we end up with the corresponding amino derivative. And this one we have seen in the previous case. So the bromine can be replaced with the hydroxide to give the corresponding phenol. And we have a phenol and the benzyl alcohol unit, which on oxidation generally undergoes only the benzylic alcohol undergoes oxidation to give the salicylic acid. So these are all the different products which are formed from this particular reactions. Now we have to convert the chlorobenzene to the compound shown here. So how to convert this one? If we look at the product, we have a phenol, we have a amino derivative. So this amino derivative can be prepared from the nitro derivative. So if we have the nitro derivative here, then we can convert them to amino, so that is possible. But how to introduce the nitro group? We have a phenol also. So should we introduce the phenol first and then nitro, or introduce nitro and then phenol? We will have to see now. So let us start with the chlorobenzene. The chlorobenzene can be nitrated to give the ortho and para dinitro derivative. So this chlorine has to be converted to the phenol. So how efficiently we can do that? Let us see. This on treatment with the sodium hydroxide gives the corresponding phenol, and the we are close enough to our final product, which is the diamino derivative. We have first introduced the OH, is introduced here. So now the nitro has to be converted to the corresponding amino derivative. So the simplest thing is to reduce the nitro group. But what reduction we can use? Can we use zinc and HCl? If we use zinc and HCl, what happens is even the OH group is lost. So although the nitro is reduced to amino, the OH is lost. So we cannot use the zinc and HCl method to convert the nitro to amino. But then how do we actually do this? To do that, the phenol only can undergo zinc and HCl reduction to give the corresponding aryl derivatives directly. The OH is lost. But if the phenol is protected as a methyl ether, here what we are doing is we are converting the phenol into the methyl ether with the treatment with methyl iodide and sodium hydroxide. This methyl ether on reduction using the same zinc and HCl condition reduces only the nitro group. So the nitro only is reduced to the amino group. The methoxy ether remains as it is, no loss of the OH group as shown here. Now our final thing is this methoxy ether has to be converted to the phenol. So treatment with the strong mineral acid produces the phenol back. So the methyl ether is cleaved to get the corresponding phenol and we end up with our final product as shown here. So this is how we can use the various reactions to prepare different compounds. How this compound can be prepared from benzene. So we need to find out what are the different methods how we have to introduce. So we have a halogen, we have a alcohol. See, the alcohol can be prepared from a ketone. So ketone means we have a acyl unit here. So if we can do a Friedel-Crafts reaction, then we can have a acyl group introduced here. But these two are now meta place. See, the main thing is bromine is an activating group which generally gives orthopara orientation. Acyl group is a meta orienting. So whether this should be introduced first or this should be introduced first is the real challenge we have to decide. So if we introduce the bromine, as I mentioned, this is an orthopara directing, so that means the acyl group cannot be introduced into the meta position, so this route we cannot follow. So then the only thing is the aromatic ring is treated, aromatic compound is treated with acyl chloride in the presence of AlCl3, that is the Friedel-Crafts reaction we carry out, and we end up with the acetophenone. So this acetyl group is meta directing, so this is what we are actually more focused on because this is a meta substituents are there in the final product. So this on treatment with bromine, that is direct halogenation, produces this corresponding bromoketone. The carbonyl group can be reduced using sodium borohydrate to the corresponding alcohol. So we can get the final product by this treatment. So the same reaction when run with ammonia instead of sodium hydroxide produces the corresponding aniline derivatives. And when the same reaction is run with the sodium hydroxide at low temperature, this we have already seen, that actually produces the corresponding phenol, and the yield, if you look at, this is very high yield. The nitroaniline is also 90%, this reaction is also 95%, so this is close to very high yield. So this mechanism actually explains how the chlorine can be replaced by the nucleophile. Additional examples are, this is a pyridine system. Here also the same reaction occurs with the chlorine being replaced by ethoxide ion, and when it is the fluorine, which is actually a very poor leaving group in the case of aromatic aliphatic nucleophilic substitution, is a very good leaving group in the case of aromatic systems. And actually
A person who discovered this reaction got a Nobel Prize for his invention. This is called Sanger reaction. So in which the dinitrobenzene, the fluorodinitrobenzene derivative, when treated with any protein, forms the DNP protein complex. And this is again hydrolyzed to give the first amino acid followed by the DNP acid. So the Sanger sequencing generally uses this reaction to sequence the amino acids present in a particular protein, and Sanger got his Nobel Prize for this particular reaction. With this, we will conclude this addition-elimination reaction mechanism. We will next move on to elimination-addition mechanism. And another example which we had already seen, we have seen with the nitro derivative, the same reaction can also be carried out with trifluoromethyl derivative. And other examples include bromine is substituted with sodamide to give anilines, para-substituted aniline, meta-substituted aniline.
In summary, we have studied few reactions of worked out examples related to conversions of aryl halides and phenols to other compounds or preparation of phenols from other aryl derivatives. With this, we conclude this session, and with this, we also conclude this particular paper completely. Thank you.